Hello everyone. I welcome you all to this digital classroom for the subject control systems. Today, I am going to give you a brief introduction about Root Locus. In the previous lecture, we have seen that the stability of any closed loop system depends on the location of the roots of the characteristic equation. Hence, for a closed loop system with a transfer function given by C of s divided by R of s is equal to G of s divided by 1 plus G of s into H of s, in which the characteristic equation is given by 1 plus G of s into H of s equal to 0. And for stability, it completely depends on the location of the roots of this characteristic equation. Hence, it is very important to know how the closed loop poles move in the S-plane. Hence, it is very important to know how the closed loop poles move in the S-plane if some of the parameters of the systems are varied. The knowledge of such movement of the closed loop poles with the small changes in the parameters of the system will greatly help us in the design of a closed loop system. Such movement of poles can be known by the root locus method introduced by W.R. Evans in 1948. This is a graphical method in which the moment of poles in the S-plane is sketched when a particular parameter of the system is varied from 0 to infinity. In the previous lecture, while we are discussing about the second order system, with respect to the parameter zeta, that is nothing but the damping ratio, we have discussed about different cases like when zeta is equal to 0, it leads to undamped. And when zeta equals to 1, we call it as a critically damped condition. And when zeta between 0 and 1, we call it as underdamped condition. And when zeta greater than 1, we call it as overdamped condition. And we have also discussed that based upon the change in value of zeta, that is a parameter of interest, we could able to see the movement of the poles in the S-plane. Let us recall once again, that is when zeta equals to 0, we have obtained two roots on the imaginary axis, that is plus j omega n and minus j omega n, exactly when zeta is equal to 0. And when zeta equals to 1, we have obtained two roots which are real and identical, that is minus omega n on the negative real axis. And when zeta between 0 and 1, while we substitute for different values of zeta, which is ranging between 0 and 1, we have obtained a complex conjugate pole at minus omega n zeta plus j omega d as well as minus omega n zeta minus j omega d. When zeta ranges from 0 to 1, we have obtained few of the roots in a particular locations like in this location, again here in this location, and on the other side in this. So we could able to see the moment of these poles exactly in these regions when we try to vary the value of zeta between 0 and 1. And if I combine all the poles, I get exactly a semicircle. And when it is at overdamped condition, that is zeta greater than 1, we could able to see the moment of poles towards the positive real axis as well as away from the positive real axis. This is for the range of zeta which is greater than 1. Hope you remember that we named it as locus of the closed loop poles of a second order system. But for root locus method, Gain is assumed to be a parameter which is to be varied from 0 to infinity. Hence, similar to that of a second order system in which zeta has been varied, now with respect to root locus, we have taken the parameter k, that is nothing but the gain, as a varying parameter, and we have to look into the moment of the poles and plot it in the S-plane for different values of k ranging from 0 to infinity. Now, let us look into the basic concepts of root locus. In general, the characteristic equation of a closed loop system is given by 1 plus g of s into h of s is equal to 0. For the root locus, the gain k is assumed to be a variable parameter and it is a part of the forward path of the closed loop system as shown in the block diagram. As two blocks are in series, I can write g of s is equal to k multiplied by g dash of s, that is a product of both the blocks, where k represents the gain of the amplifier in the forward path, or it is also called as a system gain, where k is nothing but the gain of the amplifier in the forward path, or it is also called as the system gain. The characteristic equation, after substituting for g of s in the above equation, I get 1 plus k into g dash of s into h of s equal to 0, in which we have k as a variable parameter. Now, if I vary the gain parameter k from minus infinity to plus infinity, then for each separate value of k, we will get a separate set of location of the roots of the characteristic equation. And finally, if you join all the locations of these poles in the S-plane, the resulting locus is called as root locus. In general, the variation in the gain is assumed to be 0 to plus infinity and the plot is called as direct root locus. Let us take an example here. G of s is equal to k by s. Hence, if I substitute for g of s in this characteristic equation for a unity feedback in which h of s is equal to 1, I get 1 plus k by s equal to 0. For the simplification, I get s plus k equal to 0. Hence, I get s is equal to minus k. Once after taking plus k towards the right side, I get s is equal to minus k. Hence, the roots of this characteristic equation is located exactly at s is equal to minus k. If the gain k is varied from 0 to plus infinity, the location of this roots is going to change. Hence, for this example, let us obtain the root locus. If the gain k is varied from 0 to infinity, we could able to see the location of the roots which is going to change. That is, if k is equal to 0, substitute for k is equal to 0 in this equation, hence I get s is equal to 0. When k is equal to 1, I get s is equal to minus 1. When k equal to 10, I get s is equal to minus 10. Similarly, when k is equal to plus infinity, I get s is equal to minus infinity. Now, if I plot it in the S-plane, we could able to see the change in the location of the roots. That is, when k is equal to 0, I get exactly a root at s is equal to 0. And when k is equal to 1, I get a root exactly at s is equal to minus 1. And when k is equal to 4, I get a root exactly at s is equal to minus 4. And when k is equal to 10, I get a root exactly at k is equal to minus 10. And when k is equal to plus infinity, I get a root exactly at minus infinity. Hence, by joining all the locations of the poles when k ranges from plus 0 to plus infinity, I can obtain the root locus. Hence, we can define root locus as the locus of the closed loop poles obtained when the system gain is varied from 0 to plus infinity. Hence, in this case, root locus is nothing but the negative real axis of the system. Hence, it is very clear that for all positive value of k, the system is stable. That is the moment of the pole we could able to see only in the left half of the S-plane. For all negative value of k, this system becomes unstable. If I substitute for k is equal to -1, I get a pole exactly at +1, which means that the system is becoming unstable. This is a very important point to be noted down. Hence, you can say that for all positive values of k, the system is stable. And for all negative values of k, the system becomes unstable. Let us discuss about the angle and the magnitude conditions, which are the most important criteria for root locus analysis. Now, whatever roots which are present on the root locus, it should satisfy this equation 1 plus g of s into h of s equal to 0, which is nothing but the characteristic equation, which means that each time we solve this characteristic equation and we have substituted for different values of k and we have obtained the location of the poles on the S-plane. Hence, it's very clear that whatever roots which are present on the root locus should satisfy this characteristic equation. Let us look into in detail about the concepts of angle and magnitude condition. An angle condition determines whether a point lies on the root locus or not, whereas a magnitude condition determines the system gain k for the point located on the root locus. Let me justify these 2 points. For a general closed loop system, the characteristic equation is given by 1 plus g of s into h of s is equal to 0. That is, I can take 1 towards the right side and I can write g of s into h of s equal to -1. As S-plane is complex, we can write the above equation as -1 plus 0j. That is, it is represented in rectangular form. All S values can be expressed as sigma plus j omega, where sigma represents the real and j omega represents the imaginary axis. Now let us convert the above expression into polar form and let's equate the angle and the magnitude of both sides. This gives us the condition of the root locus, which is called as magnitude condition as well as angle condition. Now let us look into the angle condition. Let me take the complex plane and here this is the real and this is imaginary axis and we have a point here -1 has been marked here and this is our point of interest and we have to calculate the angle. And if I take the path in anti-clockwise direction to reach -1, if I draw a line, if I measure the angle in the anti-clockwise direction, I get plus 180 degree. And if I go around twice, again I come back to the same place. After taking 2 more turns, then 2 times, 3 times. So it is plus 3 times of 180 degree And again, I can go around twice and I can reach the same point. Every angle represents the angle to the same point minus 1. Now it is 1, 2, 3, 4, 5. Hence it is 5 times of 180 degree and so on. Hence the angle G of s into H of s, which is equal to angle of minus 1 plus J0, will be equal to plus or minus of 2q plus 1 into 180 degree, where q is equal to 0, 1, 2, 3 and so on. If you substitute for q is equal to 0, we get plus or minus 180 degree, that is for the first case. And if you substitute q is equal to 1, we get 2 plus 1, 3 times of 180 degree, that is 3 times to reach again to the same position minus 1. And if you substitute q is equal to 2, you get 2 into 2, 4 plus 1, that is 5 times of 180 degree to reach the same point. Hence this is justified. Hence the angle condition is given by plus or minus 2q plus 1 into 180 degree. And if this angle condition is satisfied, then you can say that the point lies on the root locus. If this condition is not satisfied, then you can say that the point does not lie on the root locus. You can even measure this angle in the negative direction. So if you take the negative direction, now I get the angle as minus 180 degree as it is in the negative direction to reach minus 1. Then again you have to take 2 turns, a total of 3 turns now. Hence the angle is minus of 3 times of 180 degree, the same procedure which we followed before. And again you have to take another 2 more turns, that is minus of 5 times of 180 degree to reach the same point. Hence, we can give the magnitude condition as plus or minus 2q plus 1 into 180 degree. Plus of 2q plus 1 into 180 degree. This is the condition which has been justified in the previous slide with respect to the moment in the anticlockwise direction, and minus of 2q plus 1 into 180 degree with respect to this case which we take the clockwise direction. Hence, a point lie on the root locus when the angle suspended by the point is an odd multiple of plus or minus 180 degree. Now let us discuss about the magnitude condition. Let me take the characteristic equation 1 plus g of s into h of s equal to 0. Now if the magnitude of both sides of the equation g of s into h of s equal to minus 1 are equated, then we get a magnitude condition. Hence, modulus of g of s into h of s will be equal to modulus of minus 1, which is nothing but 1. Now in the function g of s into h of s, k is unknown, and hence we can find out g of s into h of s at a point P in the S-plane. So to determine the system gain k, modulus of g of s into h of s at s is equal to P will be equal to modulus of minus 1, where P is a point in the S-plane and which is located in the root locus. Hence, magnitude condition is used only when a point in S-plane is confirmed for its existence on the root locus by use of angle condition. Once after confirming that the point P which lies on the root locus, then we can find the unknown parameter K. Let us solve few example problems related to magnitude and the angle condition so that you will get few more confidence with respect to these concepts. Let me try with this problem. Check whether number 1 s is equal to minus 1 and the case 2 s is equal to minus 3 are part of root locus or not, and determine the system gain k for g of s is equal to k divided by s into s plus 2 into s plus 4. So you have been given with g of s. Now we are supposed to find out with respect to s is equal to minus 1, the first case, that whether it is a part of the root locus or not. So we have to make use of angle condition, and we have to find out whether s is equal to minus 1 belongs to root locus or not. And also, making use of the magnitude condition, we have to find the system gain k. Let us check for angle condition, for which at s is equal to minus 1, whether it is a part of the root locus or not. So substitute s is equal to minus 1 in the angle condition which we have proved right now with g of s at s is equal to minus 1. Hence, we get angle k divided by angle s into angle s plus 1 into angle s plus 4 at s is equal to minus 1. We have to check for whether the point s is equal to minus 1 lies on the root locus or not. So let us substitute for s is equal to minus 1 in this expression. Hence I get angle k divided by angle of minus 1 followed by angle of minus 1 plus 2 into angle of minus 1 plus 4. Hence I get angle k divided by angle minus 1 into angle of plus 1 into angle of plus 3. Let us mark for the location of minus 1 plus 3 as well as k in the complex plane. Let me locate plus 1. It lies in the positive real axis. Then minus 1, it lies in the negative real axis. Then we have k, it ranges somewhere in the positive real axis, and plus 3 exactly in this place. To measure the angle for plus 1, it is exactly 0 degree, and for k it is 0 degree, as well as for plus 3 it is 0 degree. Whereas for minus 1, we have to draw a line, and this angle will be exactly plus 180 degree if you take anti-clockwise direction, and it will be minus 180 degree if you take a clockwise direction. Let us substitute for all the angles. For k it is 0 degree divided by angle of minus 1, that is plus or minus 180 degree, into for plus 1 it is 0 degree, and again for plus 3 it is 0 degree. We have substituted for all the angles. And now we get angle 0 degree minus of angle of plus or minus 180 degree. Hence finally we get plus or minus 180 degree, which means that it is satisfying the angle condition. As I told you before, if the angle condition is equal to 2q plus 1 into 180 degree, where q ranges from 0, 1, 2, 3 and so on, then we can say that the point lies on the root locus. Hence it is very clear that s is equal to minus 1 lies on the root locus. Now let us justify for the magnitude condition and find out the system gain k. Hence you can see that s is equal to minus 1 is a point located on the root locus. Now let us find for the magnitude condition for s is equal to minus 1. Hence you know the magnitude condition, which is given by modulus of g of s into h of s at s is equal to minus 1 will be equal to modulus of minus 1. Given g of s is k divided by s into s plus 1 into s plus 4. Hence let us substitute here and replace s by minus 1. Hence we get modulus of k divided by minus 1 into 1 into 3. Hence I get k equals to 3. With respect to this case, as s is equal to minus 1 lies on the root locus, I could able to find the value of k. If the point does not lies on the root locus, then we cannot determine the value of k, remember. Let us try for the second case. So let me substitute for s is equal to minus 3 and find out for angle condition. Let us follow the same procedure. G of s at s is equal to minus 3. So let us substitute for s is equal to minus 3 in this angle condition. After substitution, I get angle of k divided by angle of minus 3 into angle of minus 1 into angle of plus 1. In the S-plane, we know the location of minus 1, minus 3 as well as plus 1. So the angle of plus 1 is 0 degree and angle of minus 1 is plus or minus 180 degree and angle of minus 3 is also plus or minus 180 degree. So let us substitute for that. I get angle of 0 degree for k, as k will be in the positive real axis, divided by angle of plus or minus 180 degree for minus 3 into angle of plus or minus 180 degree for minus 1 and 0 degree for plus 1. Hence I get angle of 0 degree divided by angle of plus or minus 360 degree. Hence I get angle of 0 degree minus of angle of plus or minus 360 degree. Hence in this case it is 2 times of 180 degree. This is very clear that it is not satisfying the angle condition. Hence, s is equal to minus 3 is not a point on the root locus. Hence, you can write that as it is an even multiple of 180 degree, s is equal to minus 3 is not a point on the root locus. Hence, system gain cannot be determined. As the previous case, s is equal to minus 1, it is a point on the root locus, hence you could be able to determine for k. Whereas in this case, as it is an even multiple of 180 degree, the angle condition is not satisfied. Hence, the gain k cannot be determined. Hope you have got a very good idea about magnitude condition and the angle condition, which is the most important criteria which is required for the analysis of the root locus. In the next lecture, let us discuss about the rules to be followed while you are sketching the root locus. Thank you.